The Mars Polar Lander and Mars Climate Orbiter missions failed. We had to get back in the saddle. We had to get something landed on the surface of Mars.
I thought it was, honestly, like a crazy idea given the amount of time that we have. The probability of failure was unacceptable.
Engineers don't like designing when there are too many unknowns.
They fooled me into taking this job, saying that, oh, it won't be that hard. It's a reflight of Mars Pathfinder. You have all the pieces there.
We knew it would be a challenge, but I don't think we adequately assessed how difficult it would be.
I think in the back of your mind, you're always prepared for anything to happen, but this wasn't one of the places that we thought something would go wrong.
Come on, man.
You don't put a system like this on a major spacecraft like this at the last moment.
The trouble is, it's great on paper, but until you put it out there and test it, you really don't know what you have.
You know, I tell my people that in terms of my top 10 list of worries, the first 3 are schedule, schedule, and schedule, and there's nothing in 4th place.
I came to the realization that the heritage wasn't in the blueprints. The heritage was in the people.
Our next pass through this, if it doesn't come together, it's an all-go-home thing. It's an over.
6 green board. 5, 4, 3, 2, 1.
At the end of 1999, the Mars Polar Lander and Mars Climate Orbiter missions failed.
I don't give net crunch stuff, but the numbers reported that they think that the signal may have been due to RFI or something in the front end. We're not seeing that in any of the other spectrums, but they're continuing to look.
JPL was responsible for these missions, and that changed everything. There was a loss of confidence. What had to be done was we had to get back in the saddle. We had to get something landed on the surface of Mars. The problem was we didn't have a lot of time. We have to go back to something we know. And what we knew is we knew the Pathfinder lander. And because of that confidence, we can do it in a short time. We got to take the Pathfinder lander and stick a rover in it.
Here we go, 6 pulses for equalization at -18 dB. Pulse number 1, 3, 2, 1, mark.
We knew at the time we had a 3-year project to go to launch, and that's just very, very tight for a mission of this kind of complexity. And we've been fighting that challenge since the beginning. You worry about, am I got the right plan? Do I really have it figured out? Are we on track? Can we stay on track?
I'll briefly go over launch, cruise, and EDL, and just give you an idea of how the downlink process works during those phases. I'll spend a lot more time on surface, specifically the tactical downlink process. I'll also talk a little bit about a couple key additional requirements for Red Rover Goes to Mars.
You start getting into this cycle of things changing just a little bit here and just a little bit there, and all of a sudden the mass got heavier, and so other things had to change. Your design heritage, the blueprint, I use the phrase that I will never use again because no one will believe me, is build to print. I said, we will take the Mars Pathfinder lander and build to print. We will take the blueprints and we will send it to the machine shop, build these same things again, and that will be the shell that we land in. And then we just have to design this rover that fits inside. That build to print concept is the one thing that was completely wrong.
Message here is if you see something that you don't like in the MER mission system design, I'm one of the people you can blame.
I came to the realization that the heritage wasn't in the blueprints. The heritage was in the people. And the people who designed this thing before, they've gone through this design work, they've experienced all the difficulties, they know how to solve it.
And then we have a final TCM at 48 hours out.
weigh 40 pounds, but they feel like 100. We are building airbag systems to cushion a rover that's going to Mars. Well, we have a deadline to meet for testing, so we have to work a lot of hours and work hard and get it done on time and make it work good, too. A lot of it is sewing through these thick layers. It's very difficult. The stuff we coat it with makes it hard to go through. We've had to get special needles, special machines, and it takes a lot of strength to press it out with your fingers and sew it. I've done both. I've worked suit parts, I've worked gloves, and I've worked these. It's like peas and carrots, you know? Gloves are more delicate, more complicated mentally, smaller. This is physically challenging because it is heavy. We have a lot of questions because in the whole time you're building it, you're wondering, is this going to be right? Is it going to be okay? Is it going to work? You can't imagine the joy. We were jumping up and down when Pathfinder landed and was successful, and that's what we want to bring into this. How would you feel if you knew that something you had actually worked on and touched every day was on Mars? Our names are on Mars because we got to sign the lander panel of Pathfinder. And believe me, we'll have our initials in some of these scenes, too.
Seriously, no. These things lose a little of their edge.
I mean, look, it's got the same texture down underneath where it's never been tested. This is the rock that was causing all the problems in the last test.
So we were right up to the hairy edge. We were supposed to just be checking the box. We were waiting to see if we had a working airbag system. It was pretty scary.
It's amazing. You never would have guessed that this rock would cause so much trouble. No, it's not. This is sharp.
They fooled me into taking this job, saying that, oh, it won't be that hard. It's a reflight of Mars Pathfinder. You have all the pieces there. Put it together again, it'll work. And every single last darn piece on that entry descent landing system had to be redesigned, sometimes almost from scratch.
So we're using the replica drop for this first drop.
MER as being this heritage, this build to print. You never get to do that.
I own the overall system responsibility, but effectively, I was more of a busybody, getting in Adam Stelson's way rather than driving the system. I wanted to see firsthand and understand the challenges. And sometimes you can't really understand it unless you're there on site and seeing all the debates that bring out those subtle nuances of the design that you do not hear any other way. We thought we understood how the airbag system was going to behave. We knew it was marginal, and nobody was expecting it to be robust. But the initial design failed and got damaged in ways we were not expecting.
45 seconds. 4 seconds. 5 seconds. 4 seconds. 1 second. Release.
Today, we tested at 16 meters per second, and it worked. I would say that, you know, on one hand, we have good reason to be excited, but on the other hand, it was expected to work at 16 meters per second. We didn't expect this one to fail.
Wow.
Just like in the movies.
Yeah.
Yeah.
Reminds me of Blade Runner.
Yeah. Yes. I remember that scene.
Resolve. Resolve.
Okay. A little bit slower.
Beautiful. Beautiful. Look at it wrinkling up. Ooh, catching. That is awesome. You can even see a piece of it. Looks like we have a clear.
The lighting's pretty hot right there.
Yeah, that's not but you know, if you back up a little bit, you can actually see an abrasion layer lifted off. It's just sitting there. That piece of abrasion layer is just sitting there.
What we've got here is what we're calling classic airbag damage, where the outermost layers are there as sacrificial elements to protect the bladder layer. It's a lot like a bulletproof vest. It gets torn up and you tear the outside part, the outer layers of the vest, and you protect the user on the inside. In this case, it's the airbag and the lander.
This tool's formal name is the rock abrasion tool. And in NASA, you have to have your name shortened to an acronym. So naturally, that makes us the creators of the RAT. I can't tell you how many suggestions I get almost daily for logos. It's a bit of a joke around here and in the space science community that we are building a RAT. One of the biggest issues facing us is the dust skirt. To prevent the dust from coming out, perhaps billowing up, and damaging the other instruments. However, it's a very slow-moving drill and only sends up small wisps of material into the air. We don't like the skirt. It's almost as like you're saying, okay, we want to eject the dust for digging this hole so we can look in, but we're building a cover right around the hole at the same time.
Sorry, your call did not go through.
We're losing money on this.
Honeybees, John Gitt. I'm here, Steve Condos.
Hi, guys.
It's me.
Yeah.
Margaret, somebody else on the line? Who else is there?
Squire said he's in another solid car, but if we yell out and we need him, he'll hear us and come back.
Okay.
That's right.
Well, you know what I recommend though? We go through the report first, and then we usually want.
Sure.
And then we do who asks questions, what's remaining, okay?
Cool.
There was a discussion that perhaps got a little persnickety because the PI on the telecom said, no, we have to keep the skirt in place and perform yet a whole nother round of tests.
But I haven't heard anything from Honeybee saying that they were going to do that.
Well, I question why bother doing that?
We don't know what the skirt does at these different angles. We don't know what happens without the skirt at these different angles. This whole thing has been sufficiently counterintuitive to me from the get-go that I'd rather see tests that that's what's going to happen.
Now, wait a minute.
Trying to sell the idea of getting rid of the skirt is going to be a lot easier if you can show that, hey, you know, this thing creates the skirt actually hurts things quite a bit. Yeah, where does the dust go? How fast, what velocity does it fly off at? Which direction is it going to go, etc.? I mean, does it fly off in a sheet, a cone?
Well, that we agree we're going to test completely thoroughly. I was just questioning continual testing with the skirt, that's all. I just didn't quite understand why that should be so extensive. We'll do it. End of discussion, okay? From their perspective, I understand, their instruments, they're worried about them, so we'll do it.
If you have a skirt, wind up mostly inside the skirt. If you don't have a skirt, then
I'm happy as a clam. However, engineers don't like designing when there are too many unknowns.
That's the baseline, and everything that these guys talked about is consistent with that budget. There's a list of threats that these guys have come to me with, and they've said, okay, the more structure may be late. The PMA contracted vol may increase. The flight software workforce may stretch to the right, et cetera, et cetera, et cetera. And I've added all those threats up. They're in the category of everything we can think of that can go wrong. Although Farouz would argue that we've made that claim before and we haven't thought of everything. I submit that based on the data I gave you this week, you can't draw that conclusion.
Cut to the quick. What is the internal processes in Division 35 to make sure that these promise dates are going to be met?
We are holding the subsystems feet to the fire as much as we can.
What part of this gives you gas? Where are you concerned? The problem the presentation presents to the board, they can't make a judgment. If they were to make a judgment, they'd say you're in very, very serious trouble.
Come on, we're not done with this review yet. Okay? I mean, we understand that problem. And if you want us to compress the story into 1 hour, we can do it.
That's not going to work here.
I mean, clearly, he does not shift his need date to the delivery date just as a matter of principle every time it happens. We go through a very long process of trying to push back on the subsystems.
The procedures have got to be more self-contained. John's right. We got to clean it up.
Mechanisms and peripherals at ACS, for example.
We are hardware and software constrained big time, and so there are probably some things we can do. There's always something you can do, but a lot of it tends to be non-critical path activities.
We have to go to some
Lousy
sites. Flat. We've had the whole mission's been around follow the water. That's what we've had that objective right from the start.
Right.
But if we go out into the middle of Elysium, we've lost that. We've lost the main objective, the main sort of theme of the mission. So it's an important issue.
For those of you who haven't been in this process before, and Ray knows well, you don't put a system like this on a major spacecraft like this at the last moment.
There's this tension that exists between the engineering team and the scientists. The engineers want success. And in order to assure success, they have to be very conservative people.
The landing system is very fragile in the presence of sustained winds. If those sustained winds go above a certain level, that the landing system, the airbags and stuff cannot do the job. And so that's another point that says that even if you don't believe the models, you better be wary of what they're saying.
And that actually changes the site selection criteria. That's the bottom line.
That's right.
You're seeing a much greater concern over winds than we even considered going in. But the way we started this was you have to certify the site as safe first.
Mm-hmm.
So I don't think...
The project will not recommend that we land in an unsafe site, regardless of the science objectives.
How do you define safe then?
That's what we're struggling with.
The struggle part is the uncertainty on your
That's
definition.
Right. Exactly.
That's exactly right, Rod.
There will always be an engineering judgment component to it.
It's not black and white. You could probably imagine two partially ordered sets. One from the scientific point of view, these are all great, these are in between, and these are not any good. And the same thing from engineering. Sure. And you can imagine lining those two up side by side and then trying to decide whether or not there existed a site that was not unacceptable from either point of view.
And this was done during Pathfinder, and Gentry was there in the very end.
MER is more complex because there were so many more data sets that you could throw at the problem. We have 2 orbiters that are going around Mars that we can direct to take pictures at target locations. So now it's much more involved. You're actually acquiring the information while you're in the decision-making process, while you're building the spacecraft, while you're worried about what the spacecraft can actually do and what sort of site it can and can't land at.
Excuse me, in terms of distant views and relief, clearly there's an issue here. But what that hematite deposit looks like on a centimeter to 10 centimeter to meter scale, nobody in this room knows. It could be wild, it could be weird, it could be very, very strange looking.
But we also heard from and let me just follow that up. Pathfinder was just as dull and boring from an orbital point of view, and we landed, there were some hills there that people got pretty excited about.
The uncertainty on this category, Matt, might rival the uncertainty on the winds.
How could that be? Scientists trying to judge what the public likes. I think you can explain this one to the public.
No way. It takes 90 days to explain it.
Oh man, if I explain Pathfinder to the public, I can explain hematite to the public. This is under the public.
No.
Wait, it was under the public category.
But it's a separate issue.
Like 15 seconds.
We have a landing site where that category is not green. I think we have a real problem.
Yes.
So.
But remember, the dynamic range is going to get opened. There may be some that have reds here.
The question I'm having is, what is the meaning of that row? And what is the meaning of good diversity? Because you can have so much diversity that you don't know what the hell you're doing.
Let's go on. Let's leave it and see if it comes to help later.
But should I put anything in the comments side about what's everyone wants?
Yeah, who thought this up?
Arthur, can you find one more person? We need another person for this thing. They lost one.
So the beginning of June of 2002, the year before launch picnic, we are 51 weeks from launch. Last week, the team went out and had a good lunch time and played a little volleyball. The schedule is the big concern on this project. You know, I tell my people that in terms of my top 10 list of worries, the first 3 are schedule, schedule, and schedule, and there's nothing in 4th place. And that's just very, very tight for a mission of this kind of complexity. And we've been fighting that challenge basically since the beginning. So the pressure now is on getting the flight equipment together through the assembly, test, and launch operations phase in order to get ready to go to Florida in March of 2003.
They owe us whatever we lose by. Donate.
The schedule situation has forced us to expend money at a greater rate than we expected, so we've had to go back to NASA headquarters and ask for an infusion of funds. They've been extremely supportive of our requests, and we've gotten everything we've asked for. But in going through that process, you worry about, have I got the right plan? Do I really have it figured out? Are we on track? Can we stay on track? My job is to make sure that the rest of the team, it's a very high caliber, very motivated group of people, can get their job done. So my job is to get the stuff that gets in their way out of the way. Keep this well-oiled machine running.
I think since this is the 0 degree, it's probably worth doing.
So I've got your concurrence that it will count as a test if it doesn't have the air data boom data.
Are you questioning whether you're going to get air data boom data?
The pilot indicates that we have a very high probability in these gusty conditions that we will smash the air data boom.
Yeah, we'll go. We will count it.
Got that, we're going.
I'm really amazed at the amount of spinning that we're getting. Well, altitude at location. Look at it. Oh. Look at that. That is splendid. Awesome. Awesome. Oh, that's fantastic.
That's great. Well, here's the thing too. If let's say this one hits and it's a good test, we quickly found out that we weren't testing them the way they should have been tested. I think in the back of your mind, you're always prepared for anything to happen, but this wasn't one of the places that we thought something would go wrong.
We went back in mid-June and had the very dramatic, complete structural failures. All right.
We're ready. Looks good. Stabilize, count, and drop. 5, 4, 3, 2, 1.
It was slightly devastating.
Significant, severe chute damage. Well, the political spin on this is pretty easy. Because this chute did not have any of the reinforcements that we put in to stop just these very kinds of failures, these kinds of failures are not surprising. And that's why we chose to use.
You got to remember, these soft goods systems like parachutes or airbags, they are not readily amenable to analysis. The inflation of a parachute is actually a chaotic event. It's a nonlinear, dynamic event, highly driven by the initial conditions of the inflation.
In that regard, I'm not surprised or disheartened at all by this. I need to get the right spin on this so that no one else chokes.
That was of a nature that just makes you're taken aback. It even takes a day or two to absorb the magnitude of what just happened. That was rough. First of all, you have to figure out why you have a failure. You have to figure out what your possible fixes are. And you don't have the schedule to investigate this in a more methodical manner that you would like.
So we have to
change our thinking on most likely the loads. And it didn't look like there was several different types of failure there. I mean, at least to me.
To me, it looked like there was.
Yeah.
But again, I'm looking through a little camera screen.
Well, even, I mean, it just, you know.
Did you hear it afterwards?
Yeah.
All right. Coming to you, Dennis. This comes for you. It's coming to you.
The fact that the parachute exploded, not a good thing.
Well, yeah, I'd rather have it happen here than
Mars.
else. Yeah.
That's right. Unfortunately, strictly speaking, that chute that just exploded was the chute that we were planning on taking to Mars. Complete structural failures. Repeated, complete structural failures of the parachute. And that was extremely distressful. I mean, that is a sense of panic, like, oh my God, what are you going to do about this? The chute failed in the correct loads. That tells us that we have a parachute that's not up to the job we need it to do. Because we have packed as much parachute as we can into the volume that's available to us, our only recourse in making the parachute stronger is to change the configuration and reduce the band length. The way you make it stronger is you put maybe other webbing or reinforcements or thicker fabric. The net result is that you need more volume to pack that fabric in. We don't have any more volume. It's going to require people to be brave, especially managers to be brave, because the certainty that we have the job done is going to come very late, and that's going to make everybody nervous. Our next pass through this, if it doesn't come together, it's an all go home thing. It's an over.
About a month ago, we began assembly, test, and launch operation. When the first part of the flight units or in our case, engineering models, are beginning to be integrated in the assembly facility where the spacecraft goes together. That's a big deal because it indicates that you now have completed enough fabrication that you can begin the test phase and begin to understand what it is we really have designed and built. And where did we build it a certain way and it behaves in a way that's unexpected, and to fix those problems so that at the end of that test period, we know exactly what the article will do so we can send it to Mars with confidence. We are doing 2 shifts per day. We started that from the very beginning. We knew it would be a challenge, but I don't think we adequately assessed how difficult it would be. I think that's been the biggest surprise.
The trouble is, it's great on paper, but until you put it out there and test it, you really don't know what you have. So our electronics are failing at our vibration tests. Sometimes we find out it's a real problem. In other cases, we realize there's nothing wrong with it at all.
There's 2 camps of assembling and testing the rovers and the spacecraft as a whole. The assembly, test, and launch operations team is assembling the flight hardware, the stuff that's actually going to go to Mars. Our area, the integration and test area, has our own lab, which is a clean room and a sandbox where we have rovers that we test in the dirt. So we receive 1 set of electronics, the brains of the spacecraft. And we plug into each connector and make sure that each connector works, and we start slowly building up a spacecraft on a tabletop configuration where then the flight software team can come in and develop the software that they need to operate each of the devices. And then as part of the test team, we start doing higher level functional tests.
The other one would verify that we didn't have a short chassis.
I like to think my job was kind of like working in the garage. It was a lot of hands-on, knowing how the vehicle operated or how the vehicle was put together. You're trying to balance all these different groups. People want to use the arm, people want to use the mast and image, people want to use both of those together. At the same time we're testing in our lab, they're putting the real pieces together. It was a lot. I mean, it was a lot of time. It was 3 shifts around the clock every weekend, and there was always somebody in the lab just because things weren't ready yet for us to start testing. And your job is just to make sure that everything works.
I look at my type, please.
Okay. There it is.
No motion at all. That thing was stable as a rock.
A little bit.
That was
Man, that thing just...
no stiffening on that at all.
Did you hear anything now?
Is there anything?
How was it, Eric?
If you get a gust of wind, the system starts to oscillate, and when you fire your retro rockets, you might impart an horizontal velocity. So you might touch down with a very gentle vertical velocity, but you might be going 30 meters per second horizontally. When we did a statistical analysis of that problem for MER, it came out that the probability of failure was unacceptable. So we needed to come out now with a solution to that problem. Camera and you take 2 pictures, and then you can look at the displacement in the 2 pictures, how much you moved, and you divide it by the amount of time between the 2 images. You can figure out how much, what's your velocity. You know, the loss of fixes, you know, were good to us. Hey, this is doable.
We are doing what is our most recent and possibly our last, actually, test taking the FIDO rover out to some mysterious field site. We do not know where. And it's a fantastic site. It's an absolutely wonderful landing site. It's got terrific geology, and best of all, there aren't any bushes. Because this rover doesn't like bushes. It's good with dirt, it's good with rocks, it's terrible with bushes because it's designed for Mars where there aren't any bushes. Or where at least it would be a real discovery if we found one.
We're going to come up with more than you can possibly execute on a drive saw. Okay? What will happen is if we get in there and we find out on the basis of UHF data that we can do remote sensing but we can't do IDD, then I'll try to get the full set.
The point of this test is to train the science team in how to do field geology with a robot that is somewhere else, and using it to simulate the kind of science that we're going to do on the Martian surface with the MER rovers. I don't know where we are in terms of latitude and longitude and what state of the United States we're in, but that doesn't matter. What we do know now is we know where we are in some synthetic orbital images. We've got images taken from overhead that simulate the kind of data that we'll have for Mars.
The SOWG meeting will begin in here promptly at 8:15. So at 8:15, I want everybody in their seats, in this room, quiet, ready to go. Which rock we choose will be influenced not just by the geology, but also by where we're going to go after that.
That's not something that comes naturally to a field geologist. We got to stay real focused on the task at hand, which is doing the best job that we can for 10 days of really simulating the science that we're going to do on Mars.
And you have all the
geology?
Yeah.
I know you guys love the PanCam. Excuse me, can I have your attention just for a moment? Yeah. I know you guys love the PanCam panorama, but don't forget one thing you've really got to focus on is what the next solid's going to be. So be looking at the current location, front has cam, so you know what's in your work body. Okay?
Good. We have 1, 2, 3, 4. Probably want to get this thing here.
Hey folks, anybody's got questions, issues on how to do naming of things? Roxana Wales here is our expert. Go to her for advice. Okay?
But so 17, 18, 19, 3 days of testing. If we really knock them out like the two in a row,
Yeah, 2 a day.
maybe make wasty, right?
Okay.
I mean, that's just the only concern is that.
Okay, so the other scenario is, then you start asking,
But
is
if
it
we
worth
could-
even getting 1 or 2 off?
And it is. It is. It's worth, look, if 1.6 fails, that's huge. And we have 3 mortars, okay? 3 GGs. Lay the parachute out like this, and we're simply going to be relying on the friction with the floor to keep it from sucking the lines into the death zone. I mean, what I'd like is to make it full inflation at center of the thing.
You just gotta just count.
You can't hit the top of the wall. So you gotta stay safely off the top of the wall, and that's it. You go that high, boom. Four, 3, 2, 1. Come on. What is that? What is that? What is that? Come on, man. I don't know what it is. What do you think it is? I've never seen that before.
We are mobilizing or scrambling all forces to have a discussion at 12 p.m. Pacific on this subject. What? Am I breaking up? At any rate, but it is a, it may be a function of the geometric porosity, the gap size.
Richard, good.
Richard, it's Robin and Trayson and Adam and Wayne is talking to Manning outside, and he'll be in a second.
Okay.
This is not anything that was seen during Pathfinder or thus far during MER's development. It just as a general policy, clamp down on the information until Robin and or I have had a chance to release a press release, essentially.
Why are we doing a press release?
Oh, and it's not a press release. The emails you receive, okay, that's how information about this drop goes out first.
because I found with the airbag drops that if you make a telephone call, somebody tells somebody else, and they play the telephone game, and by the time it makes it to up the food chain, all the good words have been lost and only the bad words have remained.
But this allows you to inform your management before it gets through the grapevine.
Yeah, wouldn't you like to tell Pete before Pete somehow found out?
Oh, no, I'm going to go tell them right now, but my point is that, you know, I'm more worried, actually it's getting to headquarters that I'm more worried about.
That's right. Okay.
Okay, because number one, I'd like to come up, I mean, I think it'd be good for us to come up there for that reason alone, is just to talk to Amy about politics of what's going on here.
Okay.
And that's one of the reasons why I want to come, is just to say, hey, you know, we probably should be with.
Here we go, baby. Arm switch on. Two, one, fire. There it goes. Look at that. Beautiful. 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 That is awesome. That was perfect. Center of the thing, everything awesome, awesome, awesome.
Oh, this is so great.
Yeah, this is totally cool.
So great.
Ah, we are so stoked. Oh, that's really nice.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, pull. 5, 4, 3, 2, 1.
Can we pull the transition through?
No.
You're a foot shy. 18 inches shy.
As soon as the transition got to the first roller, this broke.
Probably a spike in load due to the fact of trying to push all that extra around that roller.
Yeah, it's
Oh, my goodness gracious, look at that.
Oh, still is. I hope we do.
Hey, babe. How are ya? Oh, really? Oh, no. Things are couldn't be going any worse. Yeah. Oh, no, that's not clear. We're gonna decide the next half hour here what we're gonna do. And I'll call you when I find out. I love you. Bye. Oh, my little transition joint. Why couldn't you have gone a little further?
I made it.
Oh. Well, I made it.
Transition joint made it.
Test 104, Brad. That was 104.
We got to get this thing fixed because we don't have a mission without this device.
Yeah, please.
We just got to test some more.
Can you put this on a CD for me and let me take it home? This movie?
Tonight?
Yeah, let's do that then. Everybody's doing this one. Yeah, do that.
Start moving them out, guys, okay?
On the road again. Just can't wait to get on the road again. Life I love is making music with my friends. I can't wait to get on the road again.
Smile, guys, you're on candid camera.
On the road again.
Copy that, Pathfinder.
Going places that I've never been. Seeing things that I may never see again. I can't wait to get on the road again. On the road again. Like a band of gypsies, we go down the highway. We're the best.
I'll get sentimental here and break up on my last convoy. Well, we're coming to an end. We've been about 2,425 miles. We got another 150 miles or so to go, and we'll be finishing up this particular wide load convoy, which will be my last convoy over the 41 years I've worked at JPL, but it's been quite an experience. This is my 19th mission that I've worked on. Of course, the role I also used to play most of the time was a spacecraft test engineer, where I was actually out on the floor doing the electrical integration, putting the things together, and then somehow or another I started picking up doing the logistics part as far as the transportation. So my first trip down here, not convoy, but project, was Ranger 6. And that was in 1962. Things are a lot different down here than what they are now. It's been a real experience. Quite a ride. Couldn't want anything better. And now it's been documented. So I don't have to tell it over and over again. I can show them the video, right? Yeah. How about if we pull all the trucks up just side by side? Think you can do that?
I can't wait to get on the road again.
Rolling?
Here we go.
Power disable on. On in 5 seconds.
Electronics go. And hydraulics go. T-minus 30 seconds. T-minus 20 seconds. T-minus 15. T-minus 10, 9, 8, 7, 6 green board. 5, 4, 3, 2, 1. Engine start and liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
Our load relief kick rate is in. Vehicles responding. Vehicles recovering very nicely to the liftoff transient. T plus 20 seconds. Looks normal for this phase of the flight. We're approaching
go.